This video will cover graphing sine and cosine, but not only the parent functions, but we're going to be translating them. Before we get started on our PowerPoint notes, I want to show you where the graphs of sine and cosine come from. You know, back in the good old days when we were just graphing linear functions or absolute value or quadratics or even higher order polynomials, if there was an equation that you did not know for sure what the shape of the graph should be, you guys would just set up an old school T-chart like what I've got here in the middle. And you would plug and chug. You would plug the number in and chug out the outcome value, and that generates an ordered pair. With sine and cosine, it's a little bit different. I mean, not a whole lot, but we've got a whole lot of knowledge about the unit circle. So on the left-hand side, let's look at this unit circle I've drawn for us. You guys know that X and Y from ordered pairs correspond to cosine and sine. We made that connection in an earlier video. And we also know certain values of degrees on this unit circle. So for example, at 0 degrees, 0 pi, cosine of 0 is 1. Sine of 0 is 0. So if I'm making a T-chart where I plug in an X and I use sine as my function to calculate out the quote Y value of an ordered pair, that's what I'd get. What about 30 degrees? 30 degrees has a sine of 30 is 1/2. So sine of 30 is 1/2. Sine of 45 is √2/2. Sine of 60 is √3/2. And sine at 90, up there at 90, sine or my Y value is 1. So I'm only filling out the Y part of the ordered pairs because sine corresponds to the Y value of the ordered pairs. All right, so if we keep going, 120 is still a 60-degree reference, and sine of 60 is √3/2. A 45-degree reference would be √2/2, and sine of 30 would be 1/2. So this is √3/2, √2/2, 1/2, and at 80 degrees or pi, sine is 0. And that's just going to continue on around the circle, except now my sine values are negative. And I'm going to skip down to 270 degrees down there on the bottom, 3 pi/2. My sine value is -1. And when I finish out my circle at 360 degrees, my sine value is back to 0. So now let's graph those values. 0, 0 is an ordered pair. At 30 degrees, I'm at 1/2. At 45 degrees, I'm at √2/2. If you plug that into your calculator and get a decimal, it's bigger than 1/2. √3/2 is 0.8. And at pi/2 or 90 degrees, we hit the value 1. At 120, we come back down to that 0.8 value, then 0.6 or 7, I think, and then 1/2. And then at pi, we're back down here at 0. That's going to repeat itself, except on the negative direction. And at 3 pi/2 or 270, we find ourselves back down here at -1 and at 0. That is where the sine curve comes from. I'm taking the circle that we used to place on the X and Y axis, and I'm using the input for the X axis and the output for the Y axis to turn that circle into a graph of the sine wave. Let's try cosine. And I'm going to put it right next to it so we can compare. At 0 degrees, cosine is 1. And then it's root 3 over 2, root 2 over 2, 1/2. Cosine up at 90 is 0. But look, what did I forget? In second quadrant, these are negative, aren't they? And it keeps going from there. Down at 270, my cosine is 0. And then in quadrant 4, these turn back into positives, and I land back at 1 again. So let's graph our cosine parent function. Cosine at 0 is 1. And then we've got root 3 over 2, root 2 over 2. That's where sine and cosine are both equal because they're both root 2 over 2. 1/2, 0. And then we dip down into the negative area. And at pi, I was at -1. Start coming back up again here. 3 pi over 2. We're at 0 again. And land back at 1. So our cosine I know it looks a little weird. I'm trying to make it look better. It looks like a V sometimes, but it's not. There's your cosine wave. It looks a whole lot like your sine wave. If we had extended, because like if we keep going around the circle, these things keep going. And if you chose to look from pi over 2 to 5 pi over 2, that sine wave that we graphed looks a whole lot like the cosine wave, doesn't it? Yeah, it's really because sine and cosine have the same wave. It's just they have a different starting and stopping point. I mean, that makes sense, right? Because all of their values are the same. We're only dealing with 1 over 2, root 2 over 2, and root 3 over 2, 0 and 1, all the way around the circle. So that is the birth of sine and cosine. How do we actually translate that and graph it? Okay, so we're going to go back one more time, and I'm going to give you, this is where you're going to want to make sure you write this down for your parent functions. Y equals sine of x. And we start at 0, and one whole cycle ends at 2 pi. And this one started at 0. Oops, let's use a different color. Started at 0, and then our sine wave went up and hit a maximum before it came back down again at pi and hit 0. And then it went down here and hit a minimum at -1 before it came back and ended again at 2 pi. There's really important parts to the sine wave. First of all, a memory trick is I try to help you remember how to graph it, and I refer to sine when I'm trying to kind of trigger your memory of how to graph it as middle, middle, middle. because my important starting, middle, and end points are all in the middle of the wave. See this line right through here that is currently the x-axis? It cuts your wave in half. The wave oscillates over the top of this thing and underneath it, and this is called your midline. And the sine wave hits the midline, the middle, at the beginning, middle, and end. Up here, we have a maximum. Where is that maximum? Well, that happened halfway in between 0 and pi. Well, in between 0 and pi, that's pi over 2. So the division between quadrant 1 and quadrant 2. And it goes up to the point of 1. That's the biggest number on the unit circle is 1. This distance right here is called our amplitude. It also dips down to a minimum of -1, and that happened at 3 pi over 2. And we would also travel our amplitude, which is the distance of the wave, either above or below, down to the negative part, the minimum. So you can see there's 5 important pieces to the sine function. It's true for cosine. There's always 5 important parts: the beginning, middle, and the end. And then the first half has an important place. And in the second half of your wave, halfway between that, has an important spot. And let's look at cosine. Starting at 0, and 1 cycle ends in 2 pi. So let me just mention a cycle. This wave would start repeating at 2 pi. And so that's 1 cycle in the parent function is 2 pi. That's called the period. And the amplitude is the height of the wave. And for the parent function, it's 1 unit. So notice we went up 1 and down 1. So the total displacement, the total distance between the maximum and minimum is actually 2, or double the amplitude. Okay, so again, we have 3 important starting, middle, and end. And on the cosine, if you'll remember, we were up, then down, then up again. So I call cosine looks like a cup. Cup. Up, down, up. And that's how you graph it. The beginning, middle, and end, you're up, then down, then up again. And halfway in between, so right here in between quadrant 1 and quadrant 2, I hit the midline, and I do it again over here between quadrants 3 and 4. And there's my cosine parent function. So on the cosine, you have a maximum and a minimum and another maximum. And our midline intercepts happen at pi over 2 and 3 pi over 2. So those are your parent functions, and now we're going to actually start translating those and move them around. So you're going to want to pause the video at this point and write all of this down. It's super important. I cannot reduce this slide any more than I already have, it's kind of everything consolidated into one. So pause and write it down. Okay, so let's talk about each important piece. If you're given a generic function, y equals a times some trig value of bx plus or minus c, it doesn't matter which one, plus or minus d. This is how we're going to read it. Our a value is our amplitude. It's just like any other Lie coefficient in the translations we've done on parent functions before. Positive opens it up, negative flips it upside down. So a negative amplitude is going to flip our sine and cosine waves upside down. The amplitude also gives us the wave height. Not really the slope, but you can kind of understand how it would change the shape of it. The higher the wave, the more stretched out your sine wave is. And the amplitude is the height above or below the graph axis or the midline. Your B value determines the frequency. The frequency is how many waves do I get? So when we normally we look from 0 to 2 pi. So we're looking in 2 pi window. If it says the frequency is 4, I get 4 total sine waves from 0 to 2 pi. That's a bunch. Normally we only get 1. So then I would need to figure out, well, how long does it take me to end just one of those waves? Well, the total period can be calculated by 2 pi over b. That is so super important. 2 pi over b is important. That's how long it takes to complete just one cycle. Okay, your C value will shift this thing left or right, depending on the positive and negative sign. And just like with anything else, it's the opposite direction of the positive or the negative sign. So B and C work together to give you a new starting and stopping point. Instead of starting at 0 and ending at 2 pi, if this has been adjusted, we have a new starting and stopping point. So you'll find those by taking whatever's inside the parentheses, the bx plus or minus c, setting it equal to 0, and finding your new starting point. And then for the new end point, bx plus or minus c equals 2 pi, and find your new ending point. To find the middle of your graph, add start plus the end and divide by 2. And then I'm going to show you some common sense approaches to this as well when we do our example. And then lastly, the D value, it shifts your midline, or sometimes I'll refer to it as the new graph axis. Instead of it being the x-axis for the parent function, there's a new graph axis called the midline. It moves up and down the same direction as the positive or negative sign, and you will label that as y equals. Okay, so we're going to try an example. Y equals 2 sine of 3x minus pi over 2 minus 1. So we're going to label our ABCs. A equals 2, that's our amplitude. So it's going to go 2 units up and 2 units down. The total displacement from max to min will be 4 total units. My B value is equal to 3. That means I want 3 sine waves from 0 to 2 pi. So that means I have a new wavelength, or period. Period is found by 2 pi over b. So in this case, it's 2 pi over 3. Or let's convert that to degrees. Sometimes that's easier. If it's a pi over 3 radian, that is a 60-degree reference. And I want 2 of those. It says 2 of those. So 60 times that 2 is 120 degrees. Our C value is a negative pi over 2. So I know that this thing is going to shift right. And our D value is negative 1. So I know that my midline shifts down. to y equals -1. Because I have that b and c value that's been affected, I have a new starting and stopping point. So I'm going to take 3x minus pi over 2. That's the bx plus or minus c part. Set it equal to 0 so I can get my new starting point. Okay, normally in normal school years, we allow y'all, or we actually make you guys work in radians and stick to all these fraction work. But because we're cramming all of this into a small amount of time, we're allowing you to convert these radians to degrees and work in degrees. And then in the end, if you need to, you can convert back to radians. So I'm going to convert pi over 2 to 90 degrees. And my new starting point is at 30. Okay, my ending, 3x minus pi over 2 equals 2 pi. So let's convert to 90 degrees and 360 degrees. My new ending spot is 150. This is where some common sense comes in. I'm going to go ahead and calculate this middle real quick. I'm going to take my start plus my end and divide by 2. So that is 180 over 2. So my middle is at 90. Okay, so look at this for a second. If I start at 30 and we calculated that the period or wavelength was 120 degrees. So if I start at 30 and my end is 120 degrees later, I should land at 150. That makes sense. Well, if the whole wavelength is 120 degrees, then that means half of the wavelength is 60 and the other half is 60. So did I calculate that correctly? Yeah, from 30 to 90 is 60 degrees and from 90 to 150 is 60 degrees. So I'm starting at 30, I'm ending at 150, and halfway in between is 90. Now we're going to graph these things from the bottom up. So I just put my start, middle, and end, 30, 90, 150 on there. Work your way back up. Your midline is now at -1. So I need a new graph axis down here at -1. Okay. This is a sine wave. Sine is middle, middle, middle. So at 30 degrees is the starting. I'm on the midline, midline, midline. I'll make this a different color to make it easier to see. Middle, middle, middle for sine. In our parent function, from the beginning, we go up to hit a maximum. Well, we got to figure out where we go and how high when we get there. Well, then that happens right here in between 30 and 90. So the common sense approach, halfway between 30 and 90 would be 30 units, wouldn't it? So that should be at 60. If you need a formula to get to your first half, take your start plus middle and divide by 2. And we're also going to need our second half location. Well, again, these are going in increments of 30. So if we're using common sense, 30, 60, 90, that should be 120. Let's just use our formula. Middle plus end over 2 will be 90 plus 150 over 2, and that does equal 120. Okay, that's our whole timeline down there. At 60, from the axis, I go as high as the amplitude tells me to. So I go up 1, 2 units. We'll change colors again. And at 120, I'm down 2 units. And there's your new sine wave. If we're trying to compare that to the original, just so you can kind of get a feel for how much it changed. On this scale, the original sine function would have looked like that. We squished it, stretched it, pulled it down. Let's look at cosine. Same process. Amplitude is 4. My B value is 3. So the period is going to be 2 pi, excuse me, over B, which is 2 pi over 3 or 120 degrees. It doesn't always work out like that. C value is negative 5 pi over 6. So we know we've got a new starting and stopping point. And my D value is negative 2. So that means our axis shifted down. So our new midline is at y equals negative 2. So we need to calculate a new starting and stopping point. Pi over 6 is a 30-degree reference, and I want 5 of those. So that's 150 degrees. If you need a conversion factor to convert degrees to radians, you multiply by 180 over pi. That's your conversion factor. All right, so this new graph is going to start at 50 instead of at 0. Okay, let's use some common sense and see if we can get there. If we start at 50 and we know our wavelength is 120, we should land at 170 because we know we should be going 120 degrees again. So 3x minus 150 is now equal to 360. Divide both sides by 3. And you do get x equals 170. Yay! And now we need the middle. Okay, well, 50 plus 170 divided by 2. But if the whole wavelength is 120, then half the wavelength is 60 units. So hopefully when we do this math, if we start at 50 and travel 60 units, we should land at 110. So 50 plus 170 divided by 2 is equal to 220 over 2. And that is equal to 110. So we're going to start at 50, end at 170, with the middle at 110, and a new midline at negative 2. Okay, so instead of this one being middle, 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 we're dealing with cosine. Cosine is a cup. So we're going to graph up, down, up. So at 150, I'm sorry, at 50 from the graph axis, I'm going to start up the number of amplitude units. So 1, 2, 3, 4, up here at 2. If I start at -2 and travel up 4 units, I land at +2. At 110, I'm down. And then at 170, I'm back up again. So there's my up, down, up. Up, down, up. Halfway in between, I'm on the graph axis or the midline on both sections. Well, you got to know those sections. 50 plus 110 is 160. Divided by 2 is 80. Or we're traveling in 30-degree increments. And there's your graph. What I forgot to do on the last slide is you're going to have to list all your max, mins, and intercepts. So we have a maximum at 50 degrees, +2, 170 degrees, +2. You've got a minimum at 110 and -6. And then you've got midline intercepts, mid-intercepts at 80 degrees, -2, and 140 degrees, -2. So you will have to list those. That's how it's graphed. I want to go over a couple of things from your Delta math just to help make that a little bit easier. So let me pull up our Delta math real fast. The Delta math for graphing sine and cosine. Midline's pretty easy. If we go up to 4 and down to 0, that's a total displacement of 4 units. That means that my amplitude is only 2, right? And then halfway between 0 and 4 would be 2. So you'd have to type in y equals 2 for that. Ooh, there you go. Make sure to write your answer in y equals sign. Amplitude from a graph. Okay. If the maximum is at 4 and the minimum is at -4, it's a total displacement of 8. So the waves go 4 above and 4 below. That's pretty easy. The period from a graph is a little bit harder. So I like to pick from maximum to maximum. You guys can pick from midline to midline if you want to. I find maximum to maximum to be easier. So look, that maximum is at 6. And the next maximum is at 12 pi. So the distance from 6 pi to 12 pi is 6 pi units. That's how long it takes to complete one cycle of a cosine graph. The harder part is to determine period from the trig equation itself. So if you're given 4 sine of pi over 3x, your b value, your a value is 4, your b value is pi over 3. That's your coefficient of x. The formula for period is 2 pi over b. So in this example, our B value is 2. And so you'd plug that in down here for your B value to get your period. It's just a formula. You got to plug it in. These are kind of fun. You want the solid line, the parent function, to match the new function, which is the dotted line. The amplitude is usually pretty easy. That one goes up, it looks from like 2 to 4, which is an amplitude of 1, just like the parent function. But it looks like this thing is flip-flopped. So I might say that it's negative. And then I think I chose a period of 1, a frequency of 1 for all of these. And then it looks like our midline has shifted up to 3. And then look, you can try it. Whoop. Oh, we matched. Great. And then you submit it. If it didn't match, then you're going to play with those boxes a little bit. The multiple choice is super easy. And then you get to these last few problems. They are hard. So they actually want you to, it's like graphing by hand, these functions, but the instructions are a little bit confusing. I made all of my Y scales a 1, but my X axis label, well, it's easier if you make it your ending point. So on this one, there is no B or C value, so it stays ending at 2 pi. And let's see, if I want to go, boom, boom. If I want my 2 pi to end at a certain place, so I know I'm going to have a quadrant 1, middle, quadrant 2. Wait, that doesn't make sense, does it, kids? First half, middle, second half, end. Something like that. So that's my scale. And now, so now that I've got my x-axis in place, it wants me to plot the 5 important points for one cycle. So you're actually going to have to plot the max, the mins, and the axis intercepts. In this case, our axis is moved down to -4. The midline is at -4. So we're middle, middle, middle. This has an amplitude of 2, but it's negative, so it's upside down. So halfway in between. So between your beginning and your middle point, halfway in between there, we're down 2. And then we're up 2, like that. And it'll connect the dots for you to see if that's what you want to do. It's going to be easier for you to graph this on paper and then come back and try to put it on this grid. And then you can check it. And this has everything in it. It might get a little bit ugly. And like for this one with an amplitude of 24, you might want to set your y-axis in 2s, and then 2 pi over B would be 2 pi over 3 pi over 4. Which is 8 over 3, I think. So again, put 8 over 3 there. We're going to move down to -12, and that's our new thing. And this is up, down, up. So we're up 24 units. So if I start at negative 12 and I go up 24, I'm at positive 12 up. But negative 12 down, okay, I don't have enough room, do I? So I think we need to we need to reset this. So maybe we do this in terms of, what do you guys think? I don't know, 6. And this is still 8/3. Yeah, that'll do. So we're down negative 12, and at negative 12, we're up 24. So negative 12 plus 24 is a positive 12. And then halfway in between, from our new graph axis of negative 12, I'm down 24 units. So that's down here to negative 36. And then at 8/3, I'm back up again. Halfway in between, I hit the graph axis at negative 12, and there and there. It's easier on your paper, and then try to transfer it over here to this. Let me know if you guys have any questions.